Hi, my name is Mikko Suvanto, and this is the MOSOMIC MEMS Microphone Guide. This is the last episode of this series of 28 videos. In this one, I continue talking about the reliability testing of MEMS microphones. Stay tuned! This series is sponsored by Innovating Technologies. In episode 27 I talked about drop tests, vibration tests and pressure shocks. Now it's time for environmental testing. Environmental tests are used to simulate the lifetime of a microphone and test its long-term immunity to environmental factors. Typical environmental tests are done in weather chambers that allow controlling the environmental conditions. The key test parameters in weather chamber tests are temperature, humidity and time. The somewhat extreme conditions are meant to expose the microphone in a span of a few days or weeks to the same accumulated exposure it would face throughout its lifetime, starting from the microphone production line and ending in the device in the hands of the end customer. Let's have a look at some typical tests and the standards they're based on. The parameters can vary, but these give you an idea of what the tests are like. The high temperature storage and low temperature storage tests measure, like the name suggests, the microphone's ability to withstand extended storage in hot and cold environments. Typical temperatures for these tests can range from +80 to +150 degrees C for the hot storage and be about -40 degrees C for cold storage. The duration of each test can range from 72 hours to 1000 hours. In a 1000-hour test, there may be intermediate checkpoints to see how the microphones are doing, for example at 168 and 500 hours. Without intermediate checks, we wouldn't know whether the microphone failed at 1 hour or 950 hours. Since these are storage tests, the microphones are not powered on during the tests. The high temperature operation and low temperature operation tests measure the microphone's ability to operate in high and low temperatures. +125 and -40 degrees Celsius are typical temperatures used in the tests, and the duration is often 1000 hours. Since these tests simulate operation, the microphones are powered on. You can see the standards for these tests on the screen here. The temperature and humidity bias test is an accelerated live test, meaning that it simulates the lifetime exposure of the microphone to a warm and humid environment. The temperature in the test is 85 degrees Celsius and relative humidity 85%. Again, the test can take 1000 hours, possibly with intermediate checks in the middle. Like the word bias in the name suggests, the tests are done with the microphones powered on. Thermal cycle and thermal shock tests subject the microphones to alternating hot and cold temperatures. These are accelerated live tests, meaning that they simulate the lifetime exposures of the microphones to different environmental conditions. The JEDEC standard calls for 1000 cycles, -40 and +125 degrees C, the exposure being 30 minutes per cycle. The IEC standard says 100 cycles, -40 and +85 degrees C, 30 minutes per cycle, maximum change time 3 minutes, and the DUT powered off. In the humidity endurance test, the microphones are exposed to warm temperatures with high humidity. The temperatures are +30 and +65 degrees C, and relative humidity is between 90 and 93%. The test includes 18 cycles, and each cycle is 8 hours, so the total time is 144 hours. One cycle includes 4 hours in +65 degrees C and 1 hour in +30 degrees C, and the change times are 1.5 hours in each direction. The DUT power is off in this test. There are also environmental combination tests, in which microphones are subjected to a series of tests. The tests can include various combinations of, for example, temperature cycle tests, drop tests, and a humidity endurance test. After the exposure to environmental conditions, the microphones are typically allowed a recovery period, which can be, for example, 2 hours. When measured after the testing, the operation of the microphone should be the same as before the test, in other words, normal operation. The microphones are measured before the tests, so the before and after values can be compared. Some tolerances may be given for the microphone performance parameters, for example sensitivity, measured after the environmental test. The maximum allowed sensitivity change can be, for example, ±1 decibel. The pass criteria can also be as simple as the microphone must work. This means that the test looks for catastrophic failures, but is not concerned about minor loss of performance. In some cases, the test may be continued until all, or a certain percentage of, the tested microphones have stopped working. This kind of destructive testing can be used to find weaknesses in the component design. The testing can be accompanied by failure mode analysis of the tested components. Whether the microphone is powered on or not during the test can affect the results of both mechanical and environmental tests. Like I mentioned in the previous episode related to drop testing, the powering status of the component may affect the way a MEMS microphone reacts during the test, and thereby the results of the reliability test. Therefore, it should be specified in the test description whether the microphone is powered on or not. The dust and liquid tolerances of microphones are tested with contamination tests. Dust tests are often done in a box, in which the microphones are subjected to dust, the composition and particle size of which is typically specified. Dust scattering and ingress into the microphones may be accelerated with a fan, a vibration device, or by tumbling the dust box. After dust exposure, the microphones can be drop tested to test how contamination ingress can affect the reliability of the MEMS sensor. This is based on the fact that mechanical shocks can cause particles inside the microphone to move around. In some cases, the mechanical shock may cause problems, and in some other cases it may fix a problem caused by a particle, at least temporarily. The susceptibilities of MEMS microphones to liquids and other contamination that is not particles can also be tested. Depending on what the expectations for the immunities of the microphones are, the components can be exposed to, for example, everyday contamination such as water, Coca-Cola, coffee, cooking gases and greases, and so on. The results of a liquid test depend on the exposure time and how the microphone or device is exposed to liquid. For example, is the liquid splashed onto the microphone or is the microphone immersed? There's a standardized system for determining the particle and liquid ingress immunities of MEMS microphone systems in devices. The results are given as an IP rating, for example IP67. I talked about the IP rating in episode 16 when I talked about MEMS microphone protection and protective membranes used in microphone implementations into devices. One more parameter that describes the environmental sensitivities of MEMS microphones and semiconductors in general is moisture sensitivity level, MSL. The more sensitive to moisture a microphone is, the stricter the requirements are for its exposure to ambient air and moisture before it goes into the reflow oven. I talked about MSL in more detail in episode 24. ESD tests are used to test the mechanical and electrical robustnesses of MEMS microphones. Like I said in episode 9, the tests can be done in a few different ways based on international standards. ESD tests are done by subjecting the microphone to an ESD spark with the help of an ESD gun designed for this kind of testing. This can be done either as a conducted test, in which the ESD gun is in contact with the microphone onto which the discharge is applied, or by applying the shock by air. Multiple exposures are typically applied on each pad or microphone lid. The test specification should say whether the DUT power is on or off during the test. The tests are based on semiconductor industry standards, and there are 3 common models used for the testing. The charged device model simulates the discharge of a charged device when it comes into contact with a conductive material. The human body model simulates a discharge that occurs when a human touches an electronic device. The machine model simulates a discharge a microphone may get from production equipment or tools. The IEC 6100042 standard and its European equivalent EN 6100042 are other key ESD immunity standards. The discharges can be applied onto the top of the microphone, possibly attempting to hit the microphone sound port on the lid, or onto the contact pads on the bottom of the microphone. Typically, the other pads are grounded while a discharge is applied onto one pad or the lid. In component level tests, a bare microphone is tested. The tests are usually done by applying a discharge in contact with the contact pads or the lid of the microphone. In component level tests, the voltages typically vary from ±500 volts to ±8 kilovolts, depending on the test, charged device, human body or machine model. In device level tests, microphones are tested assembled into a device or a test system that simulates a device. The difference to testing bare microphones is that now the microphone is typically only exposed through a narrow sound channel. The discharges are applied as contact or air discharges, simulating a real-life discharge that can hit close to the mouth of the microphone sound channel on the cover of the device. An air discharge means that the discharge is applied with an air gap between the ESD gun and the target of the discharge. Making an air discharge hit the right place, in practice the sound channel, may be tricky. In device level tests, the discharge voltages are typically higher than in component level tests. For example, ±8 kV for contact discharges and ±15 kV for air discharges. The requirements for the type of test and the strengths of the discharges can vary depending on the case, the application, and the device manufacturer in question. To make the test results somewhat comparable with each other, the tests should be specified in detail what comes to voltage levels, test equipment, test setup, procedures, calibrations, generator waveforms, and so on. In addition to the electrical shock, an ESD spark exposes the microphone sound sensor also to a pressure shock. When the very hot discharge travels through air, it heats the air surrounding it, resulting in an explosive expansion of the air and thereby a pressure shock. The pressure pulse is loud even if it occurs in free air, but it's really loud if it occurs in the very confined space of the microphone sound channel built into the device mechanics. The sound channel directs the energy of the pressure shock directly onto the sound sensor element. The strength of the sound pressure pulse that the microphone is subjected to can easily be in excess of 10 kilopascals, and the frequency bandwidth of the pressure pulse can be much wider than 20 kHz. A surface-mounted component must naturally be reliable in reflow conditions, even if it goes through the process multiple times. Reflow tests are done simply by running the microphone on a circuit board through a standard reflow process multiple times. The maximum temperature in the test, just like in a typical standard reflow, is 260 degrees Celsius. This test is done simply to make sure that the microphone, including the package and the semiconductors in it, can handle multiple reflow rounds without an impact to performance or reliability. The microphone and/or the chips in it can be exposed to multiple reflows during the manufacturing of first the microphone and then the device. It's not uncommon that the device circuit board goes through the reflow oven twice when components are assembled and reflowed on both sides of the board. Latch Up is an inadvertent short circuit that can happen in an integrated circuit, such as the ASIC in a MEMS microphone. It's a low impedance path between the power and ground rails, which can lead to overcurrent and thereby damage to the circuit. This is naturally an unwanted phenomenon, so the Latch Up test is done to test the behavior of a MEMS microphone in circumstances that could lead to latch up. In the test, a trigger current, for example ± 200 mA, is injected into the input and output pins of the microphone. The microphone passes the test if there is no change in the supply current of the microphone after the test. The test can be done in accordance to the standard JESD-78E. A DC safety check is done to check the safety of the microphone in the case that excessive voltage is applied to one of its contact pins. The test is done by applying a high voltage to each pin of the microphone while the other pins are grounded. The voltage depends on the voltages the microphone has been designed to operate with in normal conditions. For MEMS microphones, the DC safety test voltage can be, for example, 6 volts. The microphone passes the test if smoke or fire don't occur during a 5-hour exposure. For safety's sake, the power supply output impedance must be high enough, for example 500 milliohms, and the current should be limited to, for example, 5 amperes. In addition to the reliability tests that look for reliability weaknesses and permanent damage, there are also tests that look for temporary problems that could occur when the microphone is used in real-life conditions in a device. For this, the so-called use case tests have been developed. Use case tests are meant to be a quick way to expose any problems microphones might have in relation to everyday use of the device and the microphone in it. Most use case tests can be done without big investments in equipment. There's a wide variety of things that could cause problems. They are, for example, abrupt air pressure events, ambient pressure gradients, wind, mechanical deformations or mechanical pressure, operation in hot and cold temperatures, temperature gradients, condensation, and flickering light. Many of the use cases and phenomena have been added to the list of tests at some point in the history of MEMS microphones, based on practical experiences with issues that have risen. The idea is that the microphone should operate in conditions that are considered normal without degradation in sound quality, disturbances in the signal, or significant changes to its key parameters such as sensitivity. Use case tests look for problems that occur during the exposure to the factor that might cause problems, or ones that occur immediately after the exposure has ended. This is the key difference between use case tests and other reliability tests. In other reliability tests, the microphone properties, such as sensitivity, are typically measured an hour or more after the exposure. In many cases, the method used to reveal problems is to monitor the output of the microphone during testing, either by ear or with an electrical audio analysis system. A sound source is needed next to the microphone to provide a sound input to the microphone during the test. The DUT microphone must naturally be powered during the test. If problems are noticed during the tests, the problem should be analyzed and the reason, the root cause, should be eliminated to make sure the problems won't happen in the hands of the end customer. Let's have a look at some common use case tests. First, pressure and sound sensor displacement related tests expose the microphones to pressure events and pressure gradients. These tests look for example, problems or instabilities in the MEMS ASIC system that could cause sensitivity changes or an increase in noise level from which the microphone recovers slowly. In the pressure shock test, the microphone is exposed to a pressure shock applied, for example, by putting the microphone into an airtight box and slamming the lid or door. In the tapping test, the sound port of the microphone is tapped with a finger to expose the sensor to relatively mild pressure shocks. The change of static pressure test is done in a vacuum chamber. The pressure is lowered slowly from the normal atmospheric pressure to, for example, about half of that, and then back to normal pressure. The microphone should operate normally during the test. The test looks for weird effects caused by the MEMS ASIC system in the microphone. In wind tests, the microphone is exposed to moderate and strong wind, either outdoors or in a wind tunnel if one is available. Of course, there will be wind noise in the output signal of the microphone, but otherwise the microphone should operate and capture sound normally during the test and immediately after the wind exposure ends. The temperature and humidity related tests look for temporary problems in the microphone caused by different ambient conditions. In the condensation test, microphones are cooled in a fridge, taken out and immediately exhaled on slowly. The resulting condensation on and in the microphones should not cause noises or other problems. In a temperature gradient test, microphones are subjected to a temperature gradient which should not affect the performance of the microphones. The fast rising and slow dropping temperature gradient tests can be done by first placing the microphone on a hot metal plate for 10 seconds and then taking the microphone off the plate and letting it cool down slowly. The microphone output is monitored constantly while the temperature of the microphone changes. The temperature of the hot plate can be, for example, 80 degrees C. The fast dropping and slow rising temperature gradient tests can be done in a similar way, except that now the metal plate should be cold instead of hot. The temperature of the cold plate can be, for example, -20 degrees C. Again, this test looks for problems in the MEMS ASIC system in the microphone. In the use in hot temperature test, the microphone is heated, for example up to 60 degrees C, and the output is monitored for problems. In the use in cold temperature test, the microphone is cooled down to, for example, -20 degrees C. The deformation-related tests expose the circuit board the microphone is mounted on to reasonable deformations that simulate the deformations that may happen in a real-life device. In deformation tests, a slight bending or twisting of the circuit board should not change the behavior or performance of the microphone. The constant load test means exposing the microphone to a constant mechanical load and making sure this doesn't affect the electroacoustic functionality of the microphone. The load can be, for example, 5 newtons. Another factor that can disturb a microphone is light. One probable cause for light sensitivity is the susceptibility of semiconductor devices to light. In some microphones, the need to have extremely high impedances between different parts of the electrical circuitry in the MEMS and the ASIC chips is a contributing factor. Light sensitivity can lead to disturbances, such as buzzing in the presence of flickering lights, for example, fluorescent tubes. In light sensitivity tests, microphones are subjected to a flickering light. In one of the simplest cases, the light can be a fluorescent tube that you can find on a table lamp or in the ceiling of the lab. The test can also be done in a more sophisticated way, with more accurately controllable light sources. Again, the output of the microphone is monitored for disturbances. In a light sensitivity test, it's important to distinguish between disturbances caused by light and, for example, electromagnetic phenomena. Okay, that's it for this episode, and the whole MOSOMIC MEMS microphone guide series. If enough questions arise, I may still make another video in which I address those questions. I also plan to release more content on MEMS microphones and capturing in general, so make sure you subscribe to the channel so you won't miss any of that content. Also, if you have any ideas for videos and/or you'd like to sponsor one, let me know. Thanks for watching. I hope I'll see you around. Cheers! If you have any comments or questions, write them down in the comments below and I'll do my best to answer them. You can also contact me online or on social media. If you like what you saw here, give a like for the video and subscribe to the MOSOMIC channel. That way you help me reach more people and thereby create more content. If you need more in-depth microphone training than what you saw here, contact me and we can arrange it. The training can be adapted to suit any interests and skill levels, and the customer can choose the location and duration of the course. MOSOMIC provides also consultation services in all things related to MEMS microphones. If you're a microphone buyer, I can help you select the right components for your product and manage your microphone suppliers. I can also assist in implementing the microphones into your device. For microphone manufacturers, I provide microphone marketing, product definition, product management, and development management services. I can also help you create all kinds of MEMS microphone documentation.